Okay, so let's do some examples, right? So some more interesting examples. So examples of using Cauchy's integral theorem. Okay, so number one is a pretty basic trigonometric integral. Suppose that we want to do an integral of this form. So you might say, okay, what kind of situation can I use complex analysis to do integrals? The answer is that it's not clear. It just works out. You have to have enough experience to be able to tell where you can use one and not another thing. Okay, so this is an integral where a is a real number and b is a real number, and let's take a to be greater than b to be 0. It doesn't have to be like that, but just for the sake of specific, and a of b is a real number. So can anyone do this integral without, is there a way of doing it without can you do it off the top of your head? You can go and try to do this some other time on your own without using complex analysis. And I'm not saying that it's not possible, but let me show you how to do this sort of integrals, say, using complex analysis. So you see that it's an integral over theta, and theta goes from 0 to 2 pi. That means that it's an integral. That you're doing the integral over a circle, right? So what is a circle on the complex plane? A circle on the complex plane that is, centered on the origin. So this is basically, so this integral is over a unit circle. Okay, so this is 1. So in other words, what we can say is that this can introduce a complex variable z, which is just a phase, e to the power I theta. Okay? So we are constraining our complex variable z to be a phase. The theta can be anything. Then what happens if I take dz, then I have on the right hand side, I have I e to the power I theta d of theta, right? And this is nothing but z, so I can write this as minus I d of z divided by z equal to d theta. Okay, so I can use this over here to transform this integral into a complex integral. Now next we want to replace cosine of theta by some function of z. Now if I look at this z, if I use Cauchy's famous, is it Cauchy? Cauchy's formula, right? No, Euler's famous formula, which is cosine of theta plus I sine of theta, then you might say, okay, why, the best way, the most obvious way of representing cosine of theta is to take the real part of z. But the problem with what is the problem with taking real part of z? Can someone tell me? What is the issue?
We lose the plane of, I don't know, sorry.
That's okay. Anyone else? How would you express real part of z? Z plus z bar, for example, would that be a good way of divided by 2? Would that be a good way of expressing the real part of z?
But it doesn't satisfy the sphere equations.
Exactly. It is not it's not a holomorphic or analytic function, right? So, but we have a way out. And the way out is that we are constrained to be on the circle. And on the circle, z bar is equals to 1 over z on the circle, right? Right? Because if I take z bar, then e to the power minus I theta, which according to this, the fact that we're constrained on it means that this is equal to 1 over z. So instead of replacing cosine theta by this guy, what we will do is that we shall say, okay, we are interested in only the circle, and on the circle I can represent cosine theta by z plus 1 over z over 2. If I do this, then my integral becomes a contour integral over a circle minus 2I, which comes from the measure. So this is a circle. This is S1 centered around a unit circle centered around the origin. And then d theta becomes dz, and my integrand becomes, if you just do the math, 2za plus b z squared, okay? Because if you remember, dz itself, d theta itself had a 1 over z, so we have to multiply this by 1 over z, okay? And there's a factor of 2 and all that. So now what we have to do is that we have to find the zeros of the polynomial b z squared plus 2za plus b. Yeah, right? So, of course, we know how to, this is just a quadratic equation, so we know how to do that. Then the poles are given by minus a by b plus minus square root of a squared minus b squared divided by b. Okay, we're just using the formula for the quadratic equation. But remember that we assumed a is greater than b. So, okay, so we have 2 poles. So we now have to figure out where these poles are. Like, are they both in the circle? Because if I'm going to use Cauchy's residue theorem, I have to only include the residue inside the circle. I cannot include the residues outside the circle. So we have to figure out where these poles are. Okay? And by assumption, A is greater than B. So that means that minus A by B, which is this guy over here, is less than minus 1. As well as A squared minus B squared is positive. Okay? So that means that of these 2 roots of this equation, of this polynomial, one of them, z minus, so this is negative, and this is less than, this is basically, if this is minus 1, the minus a by b is somewhere here, right? And then we are subtracting from it another positive number, right? So it's going to be even more over there. But whereas our circle has radius 1, so the circle is like this. So obviously this point is not inside the circle. Okay, so z minus is not inside the circle. Okay, so what about z plus? Maybe it's also not inside the circle. So if I now multiply z minus and z plus, and it's very easy to see that this is 1. Okay, so this means that that the modulus of z plus, because z minus is its modulus is greater than 1, then the modulus of z plus must be less than 1. And therefore, z plus must be inside the circle somewhere. We don't know where, but I don't care about that. Is the argument clear? It's just like a technical thing. Usually when you do integrals, it's very easy to find out, where the poles are.
Is this the analysis part of complex analysis?
No, this is not analysis. This is algebra.
Okay.
Okay, analysis is usually has to do with convergence, blah blah, stuff like that, right? The theorems, I think it's the theorems of complex analysis where the analysis really comes in. This is just a technical algebra. Okay? It's analysis because it involves questions of convergence, it involves integrals, as well as differentiability and stuff like that, which are stuff that you don't worry about in algebra, right? Like in linear algebra, you usually don't have to do any integrals.
Yes.
Okay, so z plus is where my so the limit. So to find the residue, I take z to z plus and multiply my function by z plus. But what is my integrand? It's minus 2a divided by z minus z plus z minus z minus. Okay, so if I put in those values, then I have minus ib divided by square root of a squared minus b squared. And therefore, the integral that I was looking for is I is 2 pi I. So the I squared minus, cancel out the minus sign, b divided by square root of a squared minus b squared. Okay? So the whole idea of using Cauchy's residue theorem to do complex integral is to actually not do any integrals. Because we're not really doing any integrals, right? We're just like figuring out the residue, which is a completely algebraic process. Okay? So any questions? Okay, so today I'm just going to give you a couple of, say, theorems that will help you, kind of see whether the integral that you're looking at is something where, this would be applicable. So this was an easy one where we didn't have to take any funny limits, but often we have to take funny limits. So